Welcome to this new session of my course, Animated Multimedia Application Design, in which we will detail the ergonomic constraints of animated multimedia applications.
In multimedia animated applications, ergonomics plays a central role in ensuring that technological sophistication translates into meaningful, usable, and satisfying user experiences. The ergonomic dimension focuses on the interaction between the human and the system, aiming to optimize comfort, efficiency, and cognitive accessibility. Unlike purely functional software, MAAs integrate multiple sensory channels, visual, auditory, and sometimes haptic, thus increasing the complexity of user interaction. This multidimensional experience requires a user-centered approach, where design decisions stem from an in-depth understanding of users' needs, contexts, and cognitive capacities. Now let's move on to the requirements specific to animated multimedia applications. In what follows, we explore the key principles that ensure these applications remain coherent, ergonomic, and truly adapted to the user. First element, the user-centered design, the foundation of ergonomic quality. A multimedia application is ergonomic only when designed around the user rather than the technology. User-centered design integrates user expectations, abilities, and limits throughout development to adapt the system to the user. In this area, we need to verify three concepts. First, understanding user needs. Users have final needs: learning, playing, or producing. An educational animation, for example, must support both comprehension and ease of interaction. Second, considering basic human activities. Multimedia applications involve essential actions such as reading, listening, speaking, or selecting. Ergonomics must harmonize these modalities to reduce cognitive load and avoid sensory overload. For instance, pairing narration with visuals but avoiding redundant text. Third, target audience and knowledge base. The interface's complexity and symbolic codes depend on users' knowledge and cultural background. Children require simple metaphors and intuitive icons, while expert tools can rely on technical terminology. Design must remain adaptive to user profiles. The second ergonomic element, the user integration throughout the design process. Ergonomic quality requires involving users before, during, and after design. Before design, gather user data and identify key tasks. During design, use prototyping and iterative evaluations to validate choices. After deployment, conduct usability tests and refine the application in real conditions. This participatory approach turns users into co-designers and ensures functional and emotional alignment with their needs. The third ergonomic element is the separation between staging and HMI scenarios. Multimedia animation relies on two complementary scenarios that must remain distinct yet coherent. The staging scenario, or content scenario, defines narrative flow and multimedia content, animations, sounds, and transitions that convey meaning or tell a story. The HMI scenario describes how the user interacts with the system through structured actions, access points, and feedback. A coherent HMI scenario ensures intuitive navigation, immediate feedback, and function access aligned with user goals. The key challenge is ensuring that narrative elements and interaction elements reinforce rather than disturb each other. The last ergonomic element is the coherence and accessibility in interface design. An ergonomic interface must provide consistent, learnable, and predictable actions. Menus, icons, and spatial organization should reflect user tasks rather than developer logic. Accessibility principles, readability, adequate contrast, appropriate animation timing, and clear audio ensure usability for diverse users, including those with sensory or motor limitations.
The communication process in multimedia applications relies on two sides, the user on one hand and the application on the other, which contains the scenes. The staging scenario, also known as the content or presentation scenario, defines the dramaturgic organization of the multimedia scenes that make up the application. It includes all elements related to the expressive and narrative composition of the system. Actors, the graphical or animated entities that perform actions or convey messages. Speech and sounds, the dialogues, narrations, or audio effects that support understanding and emotion. Decors and environments, the visual or spatial settings in which the action takes place. This scenario answers the question, what does the user see, hear, and experience as part of the story or the information being conveyed? The communication scenario describes the dynamic exchange of actions and feedback between the user and the application. It defines how the system perceives user inputs, interprets them, and responds through appropriate outputs across various communication channels. This scenario answers the question, how does the user act on the system, and how does the system react in return? The communication scenario defines the following elements: the application's dimension, whether audio-visual or haptic, the selection of devices and interfaces required to support that dimension, the organization of visual rendering to accompany actions and reactions, the arrangement of communication channels within each dimension.
The design of multimedia animated applications must address physical, cognitive, informational, and organizational ergonomics to ensure user comfort, performance, and accessibility. Physical ergonomics focuses on the relationship between the human body and the multimedia system's physical environment. In multimedia animated applications, this involves arranging peripherals such as keyboards, screens, VR headsets, and haptic devices relative to the user's posture and movements. Design should leverage human sensory and motor capacities across vision, hearing, touch, smell, and proprioception, while respecting physiological limits. Key factors include fields of perception, central and peripheral, levels of perception, such as color discrimination, sound frequency sensitivity, and tactile resolution, angles and distances of perception, which influence visibility and spatial localization, sensitivity to contrasts and brightness, thresholds of fatigue and sensory overload, and detection and interpretation of three-dimensional cues, depth, movement, and perspective. By respecting these parameters, designers ensure that the multimedia experience remains comfortable, perceptible, and non-fatiguing, particularly during prolonged use or immersive sessions. Informational ergonomics focuses on the organization and presentation of information to match the user's perceptual and behavioral tendencies. In multimedia animation, behavioral stereotypes, that is, culturally or cognitively conditioned patterns of attention and reaction, play a significant role. Users interpret visual and auditory signals according to learned conventions: red for danger, upward motion for progress, or a click sound for validation. The designer must thus anticipate and align with these expectation patterns to ensure that system messages are immediately understandable. An ergonomic interface communicates clearly, predictably, and redundantly across modalities, visual, auditory, and textual, while avoiding cognitive confusion or perceptual contradictions. Beyond individual interaction, multimedia systems are part of a larger socio-technical environment. Systemic ergonomics examines the extension of the human-machine couple to include the entire production and operational system, from software architecture and network infrastructure to teamwork organization and workflow management. This perspective recognizes that usability depends not only on the interface itself, but also on the coordination between human operators, automated processes, and digital tools, the distribution of tasks between human judgment and system automation, and the compatibility of hardware and software components.
the maintenance and adaptability of the system across contexts. In multimedia production and deployment, ergonomic design must therefore integrate both individual and collective dimensions, ensuring consistency between technical tools, organizational structures, and user practices. Cognitive ergonomics deals with the mental processes involved in interaction, including perception, memory, learning, decision-making, and problem-solving. The user's ability to process multimedia information depends on several interrelated factors. Mental workload, which increases with the complexity of tasks, the number of simultaneous stimuli, or the pace of interaction. Feedback and knowledge of results, which guide learning and self-regulation. And social and emotional context, such as the user's isolation, anxiety, or fear, which may influence attention and motivation. A well-designed multimedia system should minimize cognitive overload by organizing information hierarchically, supporting progressive learning, and providing immediate, meaningful feedback. It should also maintain an optimal balance between stimulation and control to sustain engagement without causing stress or confusion.
Here are some constraints along with their corresponding ergonomic explanations. First, minimize the number of channels. Cognitive ergonomics. This principle reduces mental load by limiting the number of simultaneous sensory or informational channels, visual, auditory, or haptic. It ensures that the user's attention is not divided among too many stimuli, improving comprehension and reaction time. Second, lighten and simplify. Do not encumber. Cognitive ergonomics plus informational ergonomics. Simplification helps reduce information density and visual clutter, making perception and interpretation easier. It prevents overload and facilitates selective attention and decision-making. Third, follow the habit and the trend. Informational ergonomics. This rule relies on behavioral stereotypes and user expectations, example, icons, gestures, menu positions. Aligning with established habits ensures intuitive use and reduces the learning curve. Fourth example, follow the scenario and accompany it. Systemic or organizational ergonomics plus cognitive ergonomics. This principle ensures coherence between the interface and the narrative flow staging scenario. The interface must accompany the evolution of content and guide user actions logically within the global system of interaction. Fifth, define the level of each action, importance, prerequisite, result. Cognitive ergonomics. This refers to the hierarchization of actions based on cognitive priority and task relevance. It helps users focus on essential operations first and understand dependencies between actions. Sixth association, action, channel, informational ergonomics. This constraint ensures that each action, example, select, validate, cancel, is transmitted through the most appropriate communication channel, visual cue, sound, or tactile feedback. It improves consistency and multimodal coherence. Seventh, channel layout, priority. Physical ergonomics plus informational ergonomics. The spatial and temporal organization of communication channels, such as screen zones, sound directions, or tactile stimuli, must respect perceptual fields and attentional priorities. It combines physical perception principles with information layout design.
Immersion in multimedia environments arises from the interaction between technology and human perception depending on presence, feeling of, being there, and interactivity, real-time user system feedback, Ergonomic factors influence both components by supporting or limiting perception, control, and engagement. First, physical ergonomics. Effect on presence. Realistic spatial correspondence between the user's body and the virtual space enhances body ownership and proprioceptive coherence. Example, correct eye-screen distance, motion tracking, haptic feedback. Poor calibration, latency, heavy devices, or uncomfortable postures break perceptual continuity and reduce the sense of embodiment. Effect on interactivity. Ergonomic interfaces reduce physical effort and reaction time, making actions feel immediate and natural. Non-intuitive controllers, fatigue, or motion sickness disrupt the fluency of interaction and limit engagement. Example, in a VR game, well-calibrated hand tracking strengthens both presence, feeling of being there, and interactivity, feeling of doing there. Second, informational ergonomics. Effect on presence. Clear, coherent, and multisensory information maintains perceptual realism and narrative continuity. Users feel embedded in a meaningful environment. Overload, inconsistency, or ambiguous cues break the perceptual frame and remind the user of the artificiality of the medium. Effect on interactivity. Information ergonomics supports intuitive comprehension of system states and available actions. Users know what they can do and how. Excessive data or complex visual hierarchies increase cognitive friction, slowing down action feedback loops. Example, adaptive soundscapes that guide attention without overwhelming the user strengthen immersion through perceptually ergonomic balance. Third, organizational ergonomics. Effect on presence. A well-organized environment, lighting, space layout, teamwork synchronization, ensures continuity between real and virtual contexts, maintaining stable orientation and comfort. Disorganization, interruptions, or mismatched contexts break the illusion of continuity, pulling the user back to the real world. Effect on interactivity. When system and user tasks are harmonized, predictable responses, efficient task flow, interactivity becomes seamless and meaningful. Technical delays, unstable networks, or incoherent task distribution introduce latency and degrade interactive fluency. Example, in a collaborative VR workspace, synchronized task management enhances both interactivity, coordinated action, and presence, shared virtual space. Fourth, cognitive ergonomics. Effect on presence. When the cognitive load is optimal, users maintain attentional focus and emotional involvement, sustaining the illusion of being in the environment. Excessive mental demand, confusion, or poorly aligned affordances cause breaks in attention, cognitive dissonance, weakening presence. Effect on interactivity. Cognitive ergonomics ensures that actions correspond to user expectations, decisions are quick, feedback is understandable, and learning is implicit. If users must consciously think about interface mechanics instead of task goals, interactivity becomes mechanical rather than immersive. Example, in an educational simulation, well-designed cognitive cues, color coding, spatial grouping, and feedback allow users to interact fluidly and remain mentally absorbed.